Welcome to This Explainer. Have you ever actually stopped to think about what sound is? And I don't just mean the music you're currently obsessed with, or the sound of my voice right now. I'm talking about the physical, totally invisible reality of it. It's actually kind of wild. Today, we're going to completely unpack how sound works, how it physically travels through the air, and how you can actually use it to calculate the world around you. Let's jump right in.
Here's our roadmap for today. We'll kick things off with the range of human hearing. Then we'll go beyond the human ear, figure out exactly how sound waves travel, look at how we shape sound with loudness and pitch, and finally, we'll calculate the actual speed of sound.
So first up, Section 1, the range of human hearing. Because honestly, before we can go out and measure a massive thunderstorm, we kind of need to understand our own biological hardware.
I want to start by asking you a deeply personal, maybe even a little surprising question. How old are your ears? And no, I definitely don't mean your biological age. I mean the functional age of your hearing. It turns out our ears actually have a very specific expiration date on certain frequencies.
Fundamentally, sound is just a form of energy that we can hear, right? It's produced by something vibrating. Most humans start out with a pretty impressive hearing range, picking up low rumbles at 20 Hz all the way up to piercing highs at 20,000 Hz. But here's the catch. As we age, those incredibly sensitive, tiny hairs inside our inner ear actually begin to physically break down. This biological wear and tear results in a gradual, irreversible loss of those higher frequencies.
When you look at real audiogram lab results, you can see the exact medical proof of this age-related hearing loss. The data typically shows a person's hearing holding perfectly steady across the lower and middle frequencies, but the moment they're tested at those extreme highs, right around the 24 kilohertz mark, the detection levels just absolutely drop off a cliff. It's a brilliant, if slightly sobering visual of our biological limits.
Moving right along to Section 2, beyond the human ear, because the sonic world definitely doesn't stop just because our inner ear hairs gave out.
To really grasp the full spectrum, we have to talk about the extremes. Sounds below 20 Hz are called infrasonic, and anything above 20,000 Hz is ultrasonic. And we don't just ignore these unheard waves. In fact, ultrasonic frequencies have massive real-world applications for us. They're heavily utilized in medical imaging, like when you use an ultrasound to look at a baby in the womb, as well as naval technology like sonar, which is used for measuring vast distances underwater. When you stack up human hearing against the rest of the animal kingdom, you realize just how incredibly narrow our 20 to 20,000 Hz band really is. I mean, elephants are out there plunging deep into infrasonic depths, picking up rumbles as low as 5 Hz. On the flip side, animals like bats and beluga whales absolutely crush our upper limits. And then you have dolphins soaring into incredible ultrasonic heights of 150,000 Hz. So with all those impressive marine mammals and nocturnal hunters in mind, what single species do you think has the absolutely widest range of hearing on Earth? You're probably guessing a dog, or maybe a bat, right?
Believe it or not, it's actually the tiny greater wax moth. This little insect possesses an absolute biological superpower. It can detect frequencies all the way up to an astonishing 300 kilohertz. That is literally double the highest frequency of a dolphin and 15 times higher than the absolute best human ear. Evolutionary biologists think they developed this insane ultrasonic hearing specifically to evade the echolocation of bats. Nature is wild, right?
Okay, now that you're totally hooked by these bizarre extremes of biology, let's unpack the underlying physics in Section 3, how sound waves travel. Because if a moth is hearing a bat, there has to be a physical medium connecting the two.
The crucial thing to know here is that sound energy travels through a medium as what physicists call a longitudinal wave. Basically, this means it works by temporarily bumping particles out of their resting spot. But unlike an ocean wave moving up and down, the particles in a longitudinal wave vibrate parallel to the direction the wave is actually moving. This constant back-and-forth motion creates alternating areas of high and low pressure in the air.
Let's make this super tangible. Picture a tuning fork. We can break down exactly how this longitudinal wave gets generated. First, you strike the fork, and those two metal tines start to vibrate rapidly. Second, as the tines push outward, they violently shove the air molecules together, creating an area of high pressure, which we call a compression. Finally, as the tines snap back inward, they pull away and create an empty, low-pressure space known as a rarefaction. This rapidly repeating push-pull sets off a literal chain reaction in the air. Think about the individual particle motion for a second. Those little air molecules aren't actually flying all the way from the tuning fork across the room to hit your ear. They are just vibrating back and forth, bumping into their neighbors like dominoes. It's the energy of those invisible compressions and rarefactions that's physically traveling across the room to eventually strike your eardrum.
Which brings us perfectly to Section 4, Shaping Sound. Let's see how all this pressure wave stuff builds into the everyday sounds you actually hear and interact with.
When we map these invisible waves onto a graph, it becomes super clear what makes them sound so different to us. Visually, we can pit a quiet, shallow wave against a loud, incredibly tall wave. We can also compare a low, spread-out pitch against a tight, high pitch. And then, we can see the difference between a perfectly smooth, pure wave, like from a tuning fork, and the messy, highly complex, layered waves produced by our human voice or a violin.
Let's lock these terms in. Amplitude is basically your volume dial. It directly determines loudness. Taller wave, louder sound. Frequency determines the pitch. More waves packed into the same space means a higher pitch. And finally, we have timbre. Timbre is the color, or the unique quality of a sound. While a tuning fork creates a perfectly uniform sinusoidal wave, an instrument like a flute or a violin adds in all these complex overtones. That's exactly why a middle C played on a piano sounds completely different from a middle C sung by a human.
All right, for a grand finale, let's step outside for Section 5, Calculating the Speed of Sound. We're going to apply everything we just learned to a real-world physics problem.
Okay, let's talk velocity. The speed of any wave depends entirely on the properties of the medium it's traveling through. For sound moving through the air, that speed is hugely dependent on temperature. The hotter the air, the faster the molecules are already buzzing around, meaning they can transmit a wave much quicker. The baseline physics formula for this is a velocity of 331.4 meters per second plus 0.606 multiplied by the air temperature in degrees Celsius. This brings us to a really cool real-world application. We all know that thunder from a lightning strike is always heard after you see the visual flash. That's because sound travels incredibly slowly compared to the absolute speed limit of light. So picture this. You're caught outside in a hot, 32 degrees Celsius Malaysian thunderstorm. Suddenly, you see a huge flash of lightning, and you count exactly 3 seconds before the thunder shakes your chest. Let's walk through the math step by step. First, we plug that 32-degree heat into our formula. We multiply 32 by 0.606 and add it to our baseline. That gives us a precise wave speed of 350.79 meters per second. That is exactly how fast that longitudinal wave is ripping through the hot air towards you. Finally, we multiply that speed by your 3-second delay. The result, that terrifying lightning bolt struck exactly 1,052.38 meters away from where you are standing. That's just a little over a kilometer.
So we've journeyed all the way from the tiny breaking hairs in our inner ear and the ultrasonic superpowers of a moth to graphing the timbre of a violin and tracking longitudinal compressions across a stormy sky. I'm going to leave you with this final thought. The very next time a severe storm rolls in, will you use this physics formula to calculate exactly how close that lightning really is? Thanks so much for joining me on this explainer, and keep exploring the invisible forces all around you.